Hey everyone, let's take a few minutes and talk about colligative properties. How do you get from road conditions like this to road conditions that look more like this? And the answer is colligative properties. Colligative properties are physical properties of a solution that depend only on the number of solute particles, meaning the type of substance that is being dissolved, not on what you're dissolving. There are three types of colligative properties: vapor pressure lowering, freezing point depression, and boiling point elevation. Vapor pressure lowering is the pressure that's exerted by the gas when it's in equilibrium, either with a solid or a liquid, in a closed container. I think a picture would probably make it a little bit easier to understand vapor pressure. So if you take a look at this microscopic view, on the left, you just have water molecules. And I think the level of liquid might be a little hard to see, but it's in between these up and down arrows. So you have evaporation and condensation happening at the same time so that it's reached equilibrium. But notice all the water molecules that are in the gaseous state. Whereas on the right-hand flask, you have maybe sugar that's dissolved in the solution. And you have the same amount of water molecules down at the bottom dissolved down here, but you have fewer gaseous water molecules up here. So that would be lower vapor pressure. And when you dissolve something into solution, the vapor pressure is lower. There are a couple factors that affect, or I guess do not affect, vapor pressure. The type of molecules that make up the solid or liquid determine the vapor pressure. If the intermolecular forces between the molecules are strong, the vapor pressure is going to be low. So, for example, water has hydrogen bonding, intermolecular forces between the water molecules. And so water might not evaporate nearly as fast as something like fingernail polish remover or acetone, where the vapor pressure above the acetone would be a lot higher because those forces holding the acetone together are weaker. On the next slide kind of shows what has no effect, and that's the surface area. If you imagine you have a test tube of water versus a container of water, the vapor pressure is going to be the same in both the test tube and the larger container. The surface area has no effect on vapor pressure. Let's talk about ionic versus molecular, also known as covalent solutes, what you're dissolving in solution. If it's an ionic solute, you have two or more ion particles or ions that are being dissolved or dissociating in solution. Molecular solutes do not break apart. They don't break into ions. And the decrease in a solution's vapor pressure is directly proportional to the number of particles that the solute makes in solution. So the more particles you have breaking apart into the solution, the more the vapor pressure is going to decrease. It's not going to evaporate as quickly. So listed here, there are three different substances. You have table salt, sodium chloride, NaCl. You have road salt, CaCl2, calcium chloride. And then you also have listed at the bottom glucose. And the question is, how many particles will each of the following salts, I guess I shouldn't say salts, only the first two are salts. Glucose is a type of sugar. And so this is, if you take a look at this, NaCl is going to break apart into Na plus and Cl minus, so two particles. Road salt is going to break into three particles. The Ca is going to have the 2 plus charge, and then you'd have two Cl negatives. And this last one's a little bit tricky unless you recognized that it is not an ionic particle. It's a molecular compound, which means it will not break up into ions. So how many particles will glucose form when it's in solution? Only one, because it does not dissociate. And the way that you can tell whether or not it is ionic or molecular is whether or not there's a metallic ion in the formula. And so for NaCl, Na would be your metallic element and Ca would be your metallic element. There is no metallic element in C6H12O6. And kind of just to check on understanding, if you had lithium chloride versus magnesium chloride, they're both ionic compounds. Between these two, which would be more effective at lowering the freezing point or raising the boiling point? And which and why did you choose the one that you did? I'll let you take a couple seconds and just think about that. Between lithium chloride and magnesium chloride, which would be more effective at lowering the freezing point or raising the boiling point? And if you said that magnesium chloride would be more effective at making the freezing point lower or making the boiling point higher, you are correct. And the reason is that MgCl2 is going to break into 3 particles. Lithium chloride is only going to break into 2 particles. The more particles it breaks up into solution, the more of an effect it has on the colligative properties. So molarity versus molality. Besides the spelling of these two similar things, what's the big difference here? So molarity is also known as molar concentration. And that's how many moles you have dissolved in a how many liters of solution. Molality, on the other hand, is how many moles you have dissolved in kilograms of solvent. So for aqueous solutions, which means water is your solvent, the difference between molar and molal solutions really doesn't make a big difference. And the reason for that is because the density of water is 1 kilogram per liter. You also know it's 1 gram per milliliter. So there really isn't a huge difference when it comes to using water for your aqueous solutions when you're comparing molarity versus molality. So when you first glance at this graph, it seems like it might be kind of overwhelming. When we're talking about freezing point depression, you know that water freezes at 0 Celsius. So if I find that up on the graph here, so that would be this point right here, the pink line, the freezing point of water would be 0 Celsius. But if you mix something in with water, whether it's salt, sugar, or some other solute, you're going to make the freezing point change. Salts are really important in Michigan because we want water to stay at a liquid state in the winter at a colder temperature. So it depends on what salt you put in with water, how much it will lower or depress the freezing point. And there is a simple formula that's listed over on the left-hand side here. And you can figure out how much that temperature is going to go down if you know the molality. That's your cursive lowercase m here. And again, that's how many moles per kilogram of water you're dissolving. And then the Kf is a constant. So for water, every molal of solution that you use, you're going to depress the freezing point 1.86 degrees for every mole of solute that you dissolve. The next slide, we're going to take a look at boiling point elevation. So similar formula, you're still going to use the moles per kilogram, the cursive M there. And I've listed the boiling point elevation constant, that's the K there, for water. So for every 1 mole of solute that you dissolve, you can make the boiling point of water a 0.5 degree higher. So if you had, and let's take a look at the graph over here. You guys all know that water is going to boil at 100 degrees Celsius. So that's where this dotted line or dashed line and the pink line meet. That would be 100 degrees. But if you dissolve a salt into your water, you can raise the boiling point. A lot of times people do this when they make spaghetti. And it's not that you're necessarily making your water boil faster, but you're allowing the water to boil at a higher temperature. Instead of water boiling at 100 degrees Celsius, you might have to get it up to 106 degrees if you've added salt to the water. So back to that constant that's over here on the left, for every 1 mole of solute that you dissolve in a kilogram of water, you can raise the temperature, the boiling point, a half a degree Celsius. So here's just a table of some common constants for freezing point depression and boiling point elevation. So you can see on the first one that water has a normal boiling point of 100. The boiling point elevation constant, like I said, is 0.51 degrees for every 1 mole of salt that you would dissolve. And for every 1 mole of salt that you would dissolve, you would lower the freezing point. You'd lower the freezing point 1.86. So if I'm looking at this over here and I only dissolved 1 mole of solute in my kilogram of water, instead of water freezing at 0 Celsius, it would freeze at negative 1.86 degrees Celsius. And then there's a couple other solvents that are listed. So you can see what the normal boiling point would be. And then when you add a solute to it, how much does it raise the boiling point? How much does it elevate it? Or how much does it decrease the freezing point? So a common practical example of this is adding ethylene glycol. We call that antifreeze to car radiators. It allows the water that's in your engine to stay liquid at a colder temperature, not freeze as quickly. We could also call this, instead of antifreeze, we could call it anti-heat, because it does just as good of job keeping the water that's in your engine from boiling, keeps it at a liquid at a higher temperature. So I hope you found this helpful. And that's our wrap up of colligative properties.